introduzimos o conceito de cociclo hiperbólico. Então, deixa eu relembrar. Nós temos o tipo de objeto que a gente está analisando fica definido por meio de uma transformação num espaço em uma função que a cada elemento desse espaço associa uma matriz invertível. E a gente considera o cociclo associado, que é a aplicação definida desse jeito. E nós dizemos que f é hiperbólico se em todo ponto x de m, para todo x de m, você pode decompor o RD como soma direta de dois subespaços, os quais podem depender do ponto x, de tal forma que essa decomposição é invariante. Isso significa que AX de EXU é o EFXU. I started in Portuguese again, right? But this part you already knew. Okay, I continue from now on. And, sorry. And, and this, so this decomposition is invariant. And moreover, there exists constants c and lambda such that the norm of A and x on EXS is smaller than c lambda n, and the norm of the inverse of the restriction to EU is smaller than c of that for every x and every n. Okay, so I want to make two more remarks about hyperbolic cycles, and when the dimension is equal to 2. Suppose A is such that so A takes values in SL2. Yeah. Suppose A from M to SL2 is such that the coefficients is continuous, and the coefficients of the matrix A of x are positive for every x. Okay, so I'm not rewriting, but maybe I should say it. M is compact, F continuous, And then I assume that A is also continuous, and the matrix have positive coefficients. Then the co-cycle is hyperbolic. This is actually useful. I mean, it's kind of curious, but it's also useful in in some of the applications. So what is the proof of this? This is a consequence, another consequence of the proposition, or maybe I could call it a corollary, another corollary of this proposition that I stated last time. The proof is, first of all, write A of x as a matrix. To say that this function is continuous is to say that these functions are continuous, that these depend continuously on the point x. So by continuity, and also, so I have A of x, B of x, C of x, D of x, bigger than some delta positive for every x. And I'm also assuming that the determinant is equal to 1. So ax dx minus bx cx equals 1. So the argument is in fact close to something that I already used on Tuesday, which is that we consider a cone, namely the cone of vectors u, v in R2, such that u and v are positive. So C is just the first quadrant here. So C. And the important observation is that since the coefficients are positive, one has that every matrix A of x sends this cone, this quadrant, inside itself. Okay, so so this cone here is mapped inside itself. But in fact, since the coefficients are not only positive, they are bounded away from 0 because they are positive and they are continuous and the ambient space is compact. So because of this bound here, it's a little exercise to check that the image of the first quadrant is contained in a strictly smaller cone, in a strictly smaller sector, like this. This angle here is related to delta. Okay. So so if we start with a vector u naught v naught in C, and we look at its image, it's going to be mapped into another vector, u1 v1, which is just A of x applied to u naught v naught. And what can we say about u1 v1? Well, first of all, these they are positive, but also we can say that so u1 is ax u naught plus bx v naught, v1 is and then there's this a simple observation that u1 v1 is So let's multiply this. What do we get? So we get ax times dx plus bx times cx u naught v naught plus something else u naught v1 plus u naught square plus something else v naught square. Okay? Just doing this multiplication. Now, I'm going to forget about these terms here because they are positive. So I can say that this is bigger, strictly bigger, than just this term. Okay? Now, this term is very similar to the determinant, except that it's actually better than the determinant. This is 1 plus 2 times bx cx. Right? Because the determinant is 1. And both these numbers, b and c, were bigger than delta. So this thing here is bigger than 1 plus 2 delta square u naught v naught. So this is a formula that I get. Now, where am I trying to get? What is my goal? I want to prove that the cocycle is hyperbolic. For that, it is enough to prove by this proposition, it is enough to prove that the norm of a n x grows exponentially. And that's what I want to do. Okay? That's what my goal. What I obtained so far is this formula here. But then, of course, I can iterate this formula by induction, and I conclude that un vn is bigger than 1 plus 2 delta square to the power n u naught v naught for every n. Right? Also, for the same reason that I started with u naught v naught here, when I iterate, I get a different vector, u1, v1 in this cone. Okay? And then, of course, I can also iterate that. So let me call this cone C prime. And what I'm saying is that the previous observations imply, first of all, this, but they also imply that the vector un vn belongs to C prime for every n. Okay? So what I want to conclude, I claim, is that un goes to infinity and exponentially, and vn also goes to infinity and exponentially. Okay? That's what I claim. I want to conclude from here. Now, I didn't say what this cone is. I don't want to have to calculate it. But it's a cone bounded by two straight lines, by half lines, that are strictly inside the first quadrant. So this is a line like V equals epsilon U. And this here is a line like U equals epsilon V, where epsilon is some small number that depends on this delta. Okay? So inside C prime, V is bounded below by epsilon U and is bounded above by 1 over epsilon U. Right? Inside such a cone where you are in the positive quadrant, but you are far away from the, you are bounded away from the axis, we have this formula here. We have such a formula. The epsilon depends on which cone that is, and that depends on delta. And you can calculate it explicitly. Okay? So, we have, the first relation there, the second relation implies that UN epsilon is smaller than Vn, smaller than 1 over epsilon UN for every n. And now I think you can see how the claim is going to come up. The product of these two grows exponentially. And they are comparable up to epsilon. So both have to grow. Okay? So this together with I, these two together, imply that UN is bigger than, let's see, Vn. Vn is bigger than it implies that UN Vn, which is bigger than 1 plus 2 delta square n U0 V0, is smaller than 1 over epsilon UN square. What did I do here? I use this inequality here. Okay, this is 1 over there, and this is this inequality. And that implies that UN is bigger than epsilon to 1/2 square root of epsilon, square root of 1 plus 2 delta square to the power n U0 V0. Analogously, just analogously, it doesn't really matter. Analogously, we have Vn, but it doesn't matter. So you call this sigma. And you call this C. And so this is saying that, well, maybe we can do it like this. Take U0 V b0 equals 1 over square root of 2, 1 over square root of 2. Then a n x of this vector, which is un, and the norm of this is, this has norm 1. That's why I chose it like this. The norm of this vector is the norm of un vn, which, as I am showing there, is bigger than c to the sigma n for this c and this sigma. Okay, so this proves that ANX grows exponentially for every n and for every x, and by the proposition that we saw last time, this implies that the cocycle is hyperbolic. Okay? This is a baby version of a big theorem called the Perron-Frobenius theorem. This is a baby elementary version where I take advantage of being in dimension 2. Okay, I'm not going to talk much about hyperbolic cocycles. I wanted to introduce them because they connect with other things that we are going to do, and I need these results. But I want to try to convince you of some, at least advertise some things. Some are good and some are bad about hyperbolic cocycles. The good things is that we can say lots of things about them. This is just an example of a property that is not obvious a priori that one can prove. So we can work them out very well. The weak things about hyperbolic cocycles is that they are very rigid objects. It's the fact that the hyperbolic cocycle exists imposes restrictions on the data, on A and on F. And that's deep, and there are many manifestations of this principle, but they are not, the examples are not necessarily very accessible. So what I'm going to do is I'm going to give you a simple elementary example to show this feature that hyperbolic cocycles are very rigid objects, and that's one of the examples in the text. There are harder and deeper examples, but this I find already very surprising. Proving that a cocycle is hyperbolic is not necessarily easy, as I said last time. So it's rather interesting that sometimes one can find very conceptual arguments to prove that a cocycle is not hyperbolic, and that's this kind of example because of all these restrictions that it imposes on the data, and that's what I want to explain now. So in this example, I'm going to consider F to be a map from the circle to the circle. Let me adjust the notation. I want it to be a map with a given degree. I have no notation for the degree. A covering map with degree k. So a covering map in this context is just the following thing: is you take the circle, and you start going around the circle here. Okay, and the condition is that as you move your point x or theta here, as you move your point here, the image should move without ever stopping, and most of all without ever reversing the direction. So one possibility is that as you move theta, the image goes around once, but it could also go around twice. Or it could go around the other way. The thing that is not allowed to do is to move and then go back. That's what covering map means in this context. Is that clear? If it's not clear, just think of the following example. The map from the unit circle to the unit circle, that the power k map. For instance, the power k map on the space of complex numbers with absolute value equal to 1. Okay, this is one example. And here k can be anything, could be positive or negative. If k is 2, for instance, that means that as you move your number here, your angle here, the image goes around twice in the positive direction. If k is -3, it means that as you move here once in this direction, the image will go around 3 times in the other direction. Okay, that's what degree k means. And now I'm going to consider a map, a function from S1 to S1, to SL2, so associating to each point a matrix. And the matrix that I'm going to consider is the following. To each theta, I associate the following matrix. Now let me write exactly. It's the product of a rotation by a hyperbolic matrix. So okay, so say 2, 0, 0, 1/2 multiplied by the rotation of angle theta. Okay? So what this means is that here, for theta equals 0, the matrix that is associated to this point is just this hyperbolic matrix. But as I move my point, I multiply the corresponding matrix at each point is the product of this by this. Okay? My claim is the corresponding cocycle, the associated linear cocycle, is not hyperbolic, cannot be hyperbolic, unless a certain arithmetic condition holds relating, unless the degree is let me see, I'm going to check, but it's unless the degree k is -1, 0, 1, or 2, I think. Yeah, something like that. Degree -1. Well, we'll see what the exact condition is when we do the argument. Okay, maybe I will have to. Only for 3 or 4 values of the degree, this can happen. Maybe those are not exactly correct, but this is no, no, has nothing to do. You can replace this by A naught, by any matrix essentially. One fixed matrix times rotation. It does depend on the following thing, and that will be obvious in the argument. It depends on the fact that as theta goes around once in the circle, the image, the matrix, goes around once in SL2. One can define that notion. SL2 is essentially the same thing as the circle. For those who know algebraic topology, what this means is that you can retract SL2 to the circle. The topology, the homology is the same, and it's the fact that this matrix, when you go around once here, goes around once here as well. Okay? In fact, the statement that I have in the book is a little bit more general, where you let you allow for other choices. But that will be clear in the proof. It's only a topological restriction, and that's the message that I want to give to you. There are often topological restrictions to uniform hyperbolicity, and this is the most elementary example that I know of. Okay, so what is the proof? Well, the proof is by contradiction. Suppose f is hyperbolic. Okay? So, by definition, at each point in the circle, we have a decomposition for each point theta in the circle. We have a decomposition of R2 into an unstable subspace and a stable subspace. I didn't say it when I defined hyperbolicity, but perhaps I should have said that automatically, this is a proposition also, or could be part of the definition, automatically the subspaces and ES theta vary continuously with theta. This is something that we may assume in the definition of hyperbolicity, or we don't assume and we prove because it's all automatically true. So let's look at one of them. It doesn't matter which one. The other one will be irrelevant. Let's look at one of them. So we have a continuous function, theta, goes to, say, the first one. It's a continuous function from where to where? Well, theta is in S1. And this is a one-dimensional subspace of R2. So this belongs to the projective space of R2. The space of lines of one-dimensional vector spaces, subspaces of R2. And I'm going to try to draw the graph of this function. So here is the graph, or an attempt at drawing the graph. This is S1 here. How should I represent the projective space? Well, projective space is essentially the circle. Okay, so I'm going to call it projective space, but it's the circle. Not exactly. There's this subtle thing that when you have the R2 and you take lines, as you go around, the angle determines the line, but in fact, a line through the origin is determined by two different angles. This angle and this one give you the same line. So, in fact, projective space is half of the circle. It's just 0 to pi, with 0 and pi identified. And that's relevant, okay? I'm going to come back to that in a minute. But for the time being, let's pretend it's a circle. Now, I don't know anything about this graph, except that it is continuous. It's the graph of a continuous function. And of course, I'm going to draw here a possible picture. Goes around, comes again. And of course, it has to close. It has to come back to the same point because this is S1. Okay? So the graph is a closed curve in this product space. And the question I'm going to ask myself is, how many times does the graph go around PR2? In this example that I've drawn here, it goes around once and twice. Maybe the answer is 0. For example, a constant would not go around at all. Okay? This is like a circle. How many times does the graph go around in the direction of PR2? It's just another way of asking, what is the degree of this map? What is the degree of this map? Okay? Well, it's certainly an integer number. And to answer this, I have to use the fact that this is an invariant subspace. So I'm going to apply here my cocycle. And so I'm going to go back to from S1 cross PR2. So when we take this and we apply the cocycle, maybe I should say this a little bit better. Wait. Let me be how many times does the graph go around PR2 when around go around PR2 when theta goes once around S1. Okay, so I'm making my question as making it more precise. I start with theta here. I move all the way once around the circle. As I do that, my subspace may or may not go around in projective space here. And I want to know how many times. Well, answer, I'm going to call that number n. Call that number It's an integer number. I'm going to show that unless k is very special, n cannot exist.
When we talk about this n, that we fixed the identification between PR2 and S1.
Yes. Yes, with PR2 with, well, I just take the elementary identification. This is R2. I take the usual basis and so on. Yes. Okay. So what do we know? After iteration, well, after iteration, if I look at the image, I apply the cocycle, the image has to be the same because the subspace is invariant. So the image has to be the same. The image under iteration is the same by invariance. But on the other hand, we have a formula here for what the cocycle does. So let's think. When, as I start moving theta here, since, well, I move theta from one side to the other, here, by f, it's going to go around, the image is going to go around k times. On the other hand, theta, f of theta, goes around the circle k times. What about a theta of e u theta? Let's consider first one simple case. Suppose, just an example to allow you a chance to do the calculation. Suppose the graph was this one. So constant. Suppose EU was constant. What is the image? How does the image look when I iterate by this cocycle? I'm taking a constant vector and I'm iterating, I'm multiplying by a matrix and the matrix is the rotation of angle theta. Okay? And then I'm multiplying by something that is fixed. If you prefer, you may also, it doesn't change to put this matrix here, and it's perhaps easy. Or think that this is the identity. Okay? So if you have something fixed, its image there is not fixed. It goes around once. This I used to call the Rubinho Barrichello lemma. There are two cars on the track. This is Barrichello, at that time used to be stopping in the track. And this is, I don't know, Schumacher. Okay? And Barrichello, with the help of the co-cycle, gets to go around here once. Here, in the meantime, Schumacher went around twice. He gets the same help as Barrichello, which means that he overtakes Barrichello twice. The two graphs cut twice here. Since this is a continuous map, and it has to cut twice over there. Okay, so what I'm trying to say is that A theta goes around the projective space once. This one comes from the help of the cocycle from R theta, plus the number of times that it went around here. The image of the blue line goes around once, and the image of the purple line goes more or less, it depends. This picture is actually wrong, because if they intersect twice here, they have to intersect twice there. Okay? So it goes around the same number of times as before, and plus the help of the cocycle. Okay? The only thing that is wrong here is the 1. It's not 1, it's 2. And the reason is that the projective space is only half of the circle. So as theta moves in the circle, this rotation goes around twice. So this is wrong. This is wrong picture, actually. I'm not sure this is clear to everyone. If you never thought about these things, this can be a little bit mysterious. I'm doing my best to try to be intuitive, but the really good way to understand this is to sit with a piece of paper, a glass of orange juice, and think. Okay? I assure you that the formula is right, so at least you have the answer, and you just have to think that actually the metaphor with Schumacher and Barrichello is fair. Okay? So what is the conclusion? On the one hand, when I move this, I get the same number of turns. So this has to be the same number, which means that 2 plus n has to be 2 plus n has to be the same number of turns that I had before, which is not n, because now I'm going around, my theta goes around k times. The clock here is k times faster. It has to be equal to k times n. So now, if you want to know the number of turns, you have to solve this equation. This equation says that n is equal to 2 divided by k minus 1. Now, n is also an integer. So this has integer solutions only if what? Only if k minus 1 is 1, k minus 1 is minus 1, k minus 1 is 2, or k minus 1 is minus 2. K minus 1 has to be a divisor of 2. And that gives the correct numbers here. And they are 2, 0, 3, and minus 1, right? Okay. Because when you tell this to anyone, you won't remember this. You'll have to do the calculation again to figure out. Okay? Now, why am I telling you this? Because I couldn't miss the occasion of stressing this fact that uniform hyperbolicity, that's at the same time as a strength and a weakness of uniform hyperbolicity, is dialogues with the topology. In this case, the topology is in this picture because I'm speaking of degree. That's where topology comes in such a way that there are sometimes unexpected obstructions to having hyperbolicity. And I said that there are deeper manifestations of this principle. A diffeomorphism is F is called a Nosov if the derivative cocycle df in the tangent bundle is hyperbolic. This is the definition. This is the definition. And then a fact, annals of diffeomorphisms exist only on special manifolds. One doesn't really know exactly which manifolds have annals of diffeomorphisms, but we know several conditions. For example, the Euler characteristic has to be 0. These are conditions on the topology. That's deeper, but it's essentially the same kind of result. For example, on surfaces, the only surface where there is an annals of diffeomorphism is the torus. Okay? Questions? Perguntas?
When did we get this 2?
The 2 is that's the term that comes from the help of the cocycle. So suppose your cocycle is constant, certain vector, and then you calculate the image under this cocycle for a constant. Okay? Now, and pretend, it doesn't make any difference. Pretend that A0 is the identity. So you're going to take this vector, and it's always the same vector. As theta varies, it's always the same vector, but you are going to rotate it by theta. Now, when you do that, theta is going to go from 0 to 2 pi. From 0 to 2 pi, you have a vector. You are taking its image under the rotation. Rotation from 0 to 2 pi, your vector is going to go around once in the plane, but in terms of the projective space, is going around twice. Okay, your vector goes, at some point it will be just opposite, and that means that it went back to itself in projective space and then completes a second turn. Okay, so this is because the map theta to r theta of v from the circle to projective space has degree 2. more informally, it's because the projective space is 1/2 of the circle. Okay? But it's clear that if that were wrong, then we would get even, this was 1, then we would get even less solutions. In any event, the principle doesn't depend on that. But that's the correct expression. Okay, I'm going to try to compensate a little bit part of the delay of the beginning. This is essentially what I want to say about hyperbolic cycles at this point, and I want to start introducing the next topic, where we will spend more time. The purpose is to prove the first theorem that I stated on Monday. But before I do that, so the purpose is to prove the following theorem. I'm not going to keep on repeating the same setting. We have a transformation. We have a function from M to GLD. And now I'm going to introduce one additional object. Given any F invariant probability measure mu in M. So maybe I should recall what this means. A probability measure. So a measure is a function. It's a function associating. I'm not going to be able to write this here. Okay, let me finish the statement and then I recall this. Given any F invariant probability measure, there exists some subset of M with full measure such that the following limit exists for every x in M naught. And this number, this limit, we call lambda plus of x. And analogously, the limit of the logarithm of the conorm also exists for every x in M naught. The theorem is not correct as I stated it, but I'm going to fill in the gaps now. Any dimension. Well, I'm not going to talk about one dimension because it's a completely different and much easier theory. And there are assumptions there that I have not written yet because I want to speak about this first. So measure means a function from B to R to 0 plus infinity. Well, probability measure from 0, 1 such that mu of the ambient space is 1, mu of the empty set is 0, and then if A1, A2, etc. are disjoint, are pairwise disjoint, then the measure of their union is the sum of the measures. For those who are not very familiar with this, I suggest taking some time this weekend to learn a little bit about the properties of measures, because I'm going to use this all the time. And Lebesgue measure on the interval, for example, is an example of this. It's the very first example. What is B? B is a family. B is a sigma algebra, a family of subsets of M closed under the map that sends undertaking the complements under this and under countable unions. If you have a countable family of elements of B, the union should be in B as well. And if you have an element of B, the complement should be in B as well. This is called a family of subsets that satisfies this is called a sigma. I'm not very interested in which sigma algebra we consider, so it's just for the sake of the definition. So I need to add an assumption there to make the theorem correct. And the assumption is that we are going to look at the functions from M to R, mapping x into the logarithm of the norm of A of x. These two functions. These two functions. Okay? We want those two functions to be integrable functions. Assume, given any invariant probability measure, such that the logarithm of the norm and the logarithm of the norm of the inverse are integrable. Okay, then the theorem is true. For example, if your function A from M to GLD is such that the matrices have bounded norm, this is automatically satisfied. Okay? I'm not going to talk at all about functions for which this is not integrable. Every time I will assume this will be a standing assumption in all the results. Okay? Pardon? No. Here M could be anything. M, B, mu is a probability space and F from M to M is a measurable function. It's completely general. And mu can be any probability measure on this probability, defined in the sigma algebra. Okay. Moreover, the theorem is not over yet. Moreover, these functions satisfy C. Lambda plus or minus of f of x is equal to lambda plus or minus of x for every x in M0. So they are invariant functions. They are constant on orbits. Okay. I can take it to be invariant. We can take it to be invariant. If you have a full measure subset, any full measure subset, and you take this, and the measure itself is invariant, and you take the set of points that never go out of M0, then this set of points whose orbits never go out of M0 will be invariant, and will still have full measure. So it doesn't make any difference. It doesn't. It's no restriction to suppose that M0 is invariant. Let's see what else. Not sure I want to state much more at this stage, but there's more. Yeah. The integral. Oh yeah, lambda plus or minus are integrable. Are integrable with respect to mu. I forgot to say it. Are mu integrable, which means that the integral is finite. Are integrable with respect to mu. And we have a formula for the integrals, for each integral. The integral of lambda plus is the infimum over n of 1 over n integral of the logarithm of an. And the integral of lambda minus is the infimum, is the supremum every time I write anything about the lambda plus, then you have a corresponding statement for lambda minus where you just replace the norm by the co-norm. Okay. So we are going to spend some time proving this theorem, and also I will observe why this theorem implies the first theorem that I stated on Monday. On Monday I was talking about picking matrices at random and multiplying them. But then when I introduced the notion of linear cocycle, I observed that one particular example of linear cocycle is precisely products of random matrices. So if you apply this theorem to that particular choice of linear cocycles, you obtain the theorem of Furstenberg as I stated it on Monday. There's only one thing that I will have to explain a little bit better, which is that on Monday, lambda plus and lambda minus were numbers, and now they are functions. Okay? Remember, there was no lambda plus of x. Okay, I'm going to come back to that, but it's no mystery. The kind of transformation, kind of system that one has in the setting of Monday are always ergodic. For ergodic systems, any function that satisfies this is constant. So in the special case of ergodic, if in particular, if the system F mu is ergodic, then lambda plus and minus are constants on full measure set M0. Okay? And that's why the X disappears. The kind of situation that we had on Monday with independent choices of matrices, the system that is involved is a Bernoulli shift. Bernoulli shifts are ergodic, so the X disappears because of this. So this is much more elementary than the theorem itself. Okay? So we'll stop here, and in the next maybe couple of lectures we'll be proving this. We'll be proving a much stronger theorem called the sub-additive ergodic theorem. More questions?